as a Sherman Fairchild postdoc in theoretical physics and astrophysics. So Eve got a lot of prestigious awards, including the Annie John Cannon Award from the American Astronomical Society, the William Dawson Scholarship at McGill University, the Mary Elizabeth Poole Prize from UC Berkeley, and a few days ago, Eve was also awarded the 2022 Vining Basham Gold Medal by the Astronomical Society of India. Which she still needs to go and pick up in India. So Eve's research specializes in theoretical studies on star and planet formation, using, like you like to say, pen and paper calculation as well as numerical simulation. So Eve is aiming to explain the measured properties of exoplanets, size, mass, and how these properties are shaped by the host star and the disk in which they form. So today, Eve will do a deep dive into the latest results in the theories of planet formation. Eve, the floor is yours.
All right. Thanks, Dimitri, for the very kind introduction. And it's really good to be back here at Caltech, and super refreshing to have this very nice sunny weather in February, which would be impossible in Montreal. So as Dimitri said, I am a theorist specializing in planet formation, and I'm particularly motivated by the observational puzzles that come about from some trends and patterns that we see in the observed properties of exoplanets. And when it comes to planet formation, the story really begins from the formation of stars. And stars form in a giant molecular cloud of gas and dust, which is a highly turbulent structure with the supersonic Mach number reaching on the order of 8 to 10. So within this cloud, you will see lots of filaments, and within those filaments themselves, you will see some local overdense clumps that can collapse under their own self-gravity. But during that collapsing process, there's also spin, which is why you end up with a spinning disk of gas and dust surrounding those protostars. And inside those disks, we see the formation of planets, which is why we call them as the protoplanetary disk. So you can actually see this disk in this beautiful JWST image going right across those dark bands, that edge-on disk. For some of these disks, where you can see more of a face-on view, you can use the radio interferometric images, like using ALMA, to get a sense of how these disks look like in terms of their structures. And very often, we see these rings and gaps that could potentially be carved out by the perturbation due to a young planet acting on the surrounding gas, and therefore also the dust. So these gas and solids provide the initial mass reservoir for planet formation, but as the planets are forming, the disks themselves are evolving as well. For example, towards the star, there is an accretion of the gas that you can see within the SCDs of young stellar objects as the excess in the UV wavelength. And on the outskirts, we expect the gas to be blown away by the winds generated by MHD processes or also by photoevaporation, so high energy photons from the central star. So that over a few million-year timescales, all the gas will be gone, and you just end up with the leftover solid material as well as the final planetary systems. So here are the measured masses and orbital periods of confirmed exoplanets, color-coded with respect to their initial detection methods. And here are the solar system planets in diamonds. Notice how there's very little overlap. So in exoplanet science, we often make a statement like how our solar system may be an outlier. We do need to be a bit careful with that statement because as of yet, we don't have access to a true solar system analog because we happen to live in a system with small planets at long orbital periods that are just really difficult to detect. But we can still say that our solar system is unique in that we don't have any of the short period planets. In particular, we have no planet with size between that of the Earth and Neptune. But it is exactly these kind of short period small planets that dominate the exoplanetary population. And with more careful statistical analysis, we now know that about 30 to 50% of all sun-like stars have at least one of these super-Earths and mini-Neptunes, with the distinction between the two being that the super-Earths are the scaled-up version of the rocky Earth, so size between about 1 to 1.8 Earth radii. Mini-Neptunes are the scaled-down version of the Neptune, so with some gaseous envelope, with size between about 1.7 to 4 Earth radii. By comparison, the large planets, the gas giants, they are easier to detect, but they are much rarer. Only about 1% of sun-like stars have these hot Jupiters. What is striking, however, is that at any given orbital period, we have this full gamut of possible class of exoplanets, which is particularly striking if you go back to the mass diagram and notice how we have at least 4 orders of magnitude range in possible masses at a given orbital period. So how can we understand this huge diversity? What are the key parameters that control whether a planet remains rocky or emerges as gassy? And once we identify those parameters, how can we use them to understand some of the intriguing patterns and trends that have emerged in modern observations as we focus on individual classes of exoplanets, like this radius gap that separates the smaller rocky planets versus the more gas-enveloped mini-Neptunes, and this observed peak in the gas giant occurrence rate that seems to suggest that these giants like to appear, they have this preferred location between 1 and 10 AU. So what is so special about that particular location? So we'll begin this discussion by first identifying these key parameters. And because the question here is to understand the origin of the spectrum from rocky to gassy, we're really asking the question about how rapidly can a planet grow their gaseous envelope. So let's begin with the picture where we have this rocky core that have emerged by coagulation of solid material within the disk. And this core is massive enough that you can define some gravitational sphere of influence, which is just minimum between the boundary and the Hill radius. So within the sphere, you can bind the gas to the gravitational potential of this core, and that binding process, that release of potential energy, creates a non-zero temperature gradient. And when you have a gas layer with non-zero temperature gradient, that gas layer would like to cool in an attempt to erase that temperature gradient. And a cooling gas layer will contract. That allows for the accretion of even more gas to fill up this space. So using this simple cooling physics, you can write down analytically the scaling relationship between the envelope mass fraction and some physical parameters. So let's begin by writing down the accretion rate, setting that equal to the cooling timescale, so accretion timescale to the cooling timescale, which is given by the internal energy divided by the cooling luminosity. Now, throughout this entire cooling process, that envelope remains in hydrostatic equilibrium. In other words, the sound crossing timescale is much, much shorter than the thermal timescale. And for an envelope in hydrostatic equilibrium, to order unity, their internal energy will be given by the gas mass sitting in the gravitational potential of the core. Now, in terms of cooling luminosity, let's take a closer look at the thermal structure of this envelope. So in almost all cases, you have the outer radiative zone and the inner convective zone. And the reason for that is as you go towards a deeper and deeper layer, you hit about 2500 Kelvin, That's when you start dissociating hydrogen molecules. And when you have free hydrogen atoms, then you can start making H- ions, whose opacity is a very strong function of temperature. So it becomes a dominant source of opacity. And as you go to even deeper layer, the opacity just shoots up, so much so that this inner layer is so opaque that the radiative diffusion is no longer an efficient mode of energy transport. So convection prevails on the inside, and furthermore, this dissociation of hydrogen molecules require energy. That causes a thermostatic effect where you have a decrease in the adiabatic index to the point where you have a centrally concentrated envelope. And about 90% of all the gas is locked into this inner convective zone. Then the bulk cooling timescale of this envelope is just given by the cooling timescale of this convective layer. And when it comes to convective energy transport, you might recall that the rate of that energy transport is set by the thermodynamic properties right at the lid of that convective layer. So there are various ways that you can explain that, but I think one of the best ways to explain is to come up with an everyday analogy and try to come up with a demo. So here's a demo that I made a while ago, but it's so simple to make and quite effective that I reenact this every time I teach a fluids class. So let's see if I can play it. Okay. So this is just hot tea in a glass, and I'm pouring cream so that I can use it as a tracer of convection. If you decide to try this on your own, which is really simple to do, it's really important that you fill right up to the brim, to really fill up that glass. So I'm just waiting for the sloshing to die down. The reason why it's so important to fill up right up to the brim is because we're going to try to control the temperature by putting metallic lid on top and put ice cubes on top of it. This sloshing motion, that up and down, that is not convection. That's the surface gravity wave that I've generated by pouring the cream. So I've placed the metallic lid. I just placed one ice cube. That was the second ice cube. Notice what happens to the cream. It rises up. I hope you can actually see it. So it rises up, and within a few seconds, there's almost a complete mixture of the tea and cream. And it's a bit hard to see on the screen, but I actually just placed a third ice cube, and you can see that the convective motion here became a lot more vigorous. All right, so you can have this full mixture of the tea and cream without any stirring, just put ice cubes on top of it. All right, so this is a demonstration that it is the conditions right at that boundary, right at the lid, that triggers this convective motion. And of course that makes sense because really all I've done here is I have set up a steeper temperature gradient, which is a requirement for the triggering of convective instability. Okay, so by analogy, for the exoplanet envelope, it is the conditions right at this radiative convective boundary that controls the rate at which the energy can be transported out of that inner convective zone through the boundary and into the radiative layer. So then we can write down this cooling luminosity in terms of the conditions right at that boundary. And by definition, because we're right at that boundary, we can write down this cooling luminosity due to radiative diffusion at the radiative convective boundary, which scales as photon mean free path, inverse with density, inverse with gas mass, and combining everything together, you can write down that the gas mass would grow as a square root of time. But of course, this also depends on opacity, which itself is a function of density and temperature. So with more careful calculation, you can derive the full scaling relationship to identify the 3 key parameters that control how thick of an envelope you're going to end up with. If you're wondering how I got this numerical coefficient, this has been calibrated to the detailed numerical calculation solving one-dimensional structure equations. So, more time you have to build your envelope, you are going to end up with thicker envelope. The more massive the core you have, the easier it is for that core to hold on to a thick envelope. And the less metal you have within your accreted gas, the less opaque it is, easier to cool, easier to accrete. Notice that by far, it is the mass of the core to which the envelope mass fraction is the most sensitive. So for the first part of our discussion, we're going to focus on the properties of the core, how massive they are, and when exactly they assemble with respect to the finite disk lifetime. And later on, when we talk about the gas dry ion occurrence rate, we're going to come back to the effect of the metallicity. Now, there are 2 limits where the simple scaling relationship breaks down. The first is at the high mass end, where if you have big enough, massive enough core, then you can easily reach a point where your envelope mass becomes comparable to the core mass. So this is the classic runaway gas accretion theory. And once you reach that point, you're dealing with the self-gravity of the envelope becoming important. And in particular, you have this massive envelope that you need to maintain this hydrostatic equilibrium. So you need large cooling power, which means you have accelerated the cooling process and therefore the gas accretion process. And you just made the problem worse by accreting even thicker and heavier gas. And you just keep making the problem worse and worse and worse, until you have the catastrophic shortening of the cooling time and therefore a super exponential growth of the gas mass and therefore the total planetary mass. So this is a classic solution for the formation of gas giant, including our Jupiter. Just need to keep in mind that this obviously does not go to infinity because there is some finite mass reservoir, but in particular, eventually this will be limited not by thermodynamics, but by hydrodynamics. So basically the rate at which the disk can globally deliver the gas to the vicinity of the planet, so the global disk accretion rate. On the opposite end, at the low mass end, this is another limit at which that simple cooling scaling relationship breaks down. So when I say low mass, I'm talking about something smaller than about 1 to 2 Earth masses, with the exact number depending on the orbital period. So at that point, the core is so small that you can easily reach a point where you have completed your cooling process, where you have completely erased away that initial temperature gradient. So your entire envelope just thermally relaxed to the outer nebula. You have an isothermal profile, and you're done. No more cooling, no more accretion. And we know how to write down that, that mass that is relevant for the isothermal envelope. It is exponentially dependent on the core mass. So combining everything together, here's the expected envelope mass fraction as a function of core mass, color-coded with respect to the different times at which the cores could have assembled, where the yellow points are the ones that have assembled so early that they have the full disk lifetime to build their gaseous envelope, whereas the purple points are the ones that have assembled so late that they barely had any time to build their gaseous envelope. So that accretion time gives you this large scatter for a given core mass, but notice how there's a very stringent upper envelope that is a strong function of the mass of the core. And this comes from those different limits on the gas accretion. At the low mass end, this comes from that isothermal limit. We transition to that cooling curve that we have derived, transition to the runaway regime, and a halting by the global disk accretion. So, as a theorist, I can give you the envelope mass fraction for a given core mass and for a given time, but observers have access to the size of the planets and the total mass of the planets. Luckily, there's almost one-to-one relationship between the envelope mass fraction and the measurable size of the planets. So the more gas-rich planets, those are the gas giants. And if you fall between about 0.1 to 10 to negative 4, 10 to negative 5, those are your mini Neptunes. If you fall below 10 to negative 4, 10 to negative 5, you have such a thin atmosphere that your size will be dominated by the size of the core. So you have a practically rocky super-Earths. Now, where I would like to draw your attention is the fact that these gas giants occupy a very small region of this parameter space. That means these giants have a very stringent formation condition. Not only do their cores have to assemble early, but they also have to be quite massive, so greater than about 10 Earth masses, as compared to their smaller counterparts that have no restriction on core mass. They just have to assemble relatively late. And this stringent formation condition for these giants may be the reason why they are so much rarer as compared to their smaller counterparts. And this stringent formation condition also manifests in the observed trends between the planet population and the properties of the host star, like the metallicity. And the logic here is that it is more likely that you create this more massive cores within more metal-enriched disks. And at least at a bulk sense, we would expect to find more metal-rich disks around metal-rich stars. So with that one-to-one correlation in mind, because these small planets can emerge over sort of this full range of possible core masses, we would expect very weak, if any, dependence of their population on the host star metallicity. As compared to the giants, because of that stringent formation condition, we would expect a strong dependence on metallicity. And we already knew that observationally back in the early and mid-2000s. With more modern observations, we now have access to the small planet population, and indeed, their occurrence rate is a lot less sensitive to the stellar metallicity as compared to this larger gas-rich planets. So there seems to be some good agreement between what is currently observed to what we might expect from this simple gas accretion physics. So with that in mind, let us now zoom in to individual classes of planets and talk in more detail about some of the trends and patterns that have emerged. Let us start with the small planets, which show this very clear gap in the radius period space that separates the rocky planets from the more gas-enveloped mini-Neptunes. And I should really preface by saying that my theorist colleagues have made a prediction for this, for the existence of this radius gap, which is quite rare in our field at the moment. And this comes from the theory of photoevaporative mass loss, where the idea is that all the planets were originally this gas-enveloped mini-Neptunes, and those that were close to the star were particularly susceptible to mass loss due to the high stellar flux, especially in the X-ray and UV wavelengths. So those high-energy photons ionize the upper layer, thermalizes the surrounding gas, and drives off the wind, transform the short-period mini-Neptunes to short-period rocky planets. There's a second flavor of mass loss called the core-powered envelope mass loss, where here the idea is that there's not just heating from above, from the star, but also heating from below. So the core cools off, and that would transfer heat to that surrounding upper gaseous envelope. And that will puff up the planet out to the sonic radius, and then you can calculate the classical Parker-Winn solution to compute the mass loss rate. And that mass loss rate depends on the sound speed at the sonic radius, which depends on the equilibrium temperature, which depends on the bolometric flux of the star. So because they both depend on the stellar flux, you expect a very similar pattern, the transformation of the short period gas-enveloped planets to short period rocky planets. So they both do a really good job at reproducing the general shape of the radius gap, but they also expect very few long period rocky planets, which includes our solar system. But even in exoplanetary system, we have some evidence that these long period rocky planets may exist and may even be dominant. So is there a way to reconcile these two features? And what I'm going to show you is that you can reproduce this radius gap very robustly even before any sort of mass loss, just using that gas accretion physics we've just discussed. And also reconcile that with this long period rocky planets. So let's go back to the expected gas mass for a given core mass. We've seen this plot before. The only difference here is I'm varying the orbital periods. So as we have seen before, we see this very much different regimes of the shape of the gas mass versus core mass. As a reminder, this steep drop-off is from that isothermal limit, and then transition to the cooling curve, little bit of a runaway until you're halted by the disk accretion. If you're wondering what's going on over there with a little bit of an increase, that is due to the fact that these are such massive cores that even from the very beginning, their gas accretion was limited by the global disk accretion, which itself is a time-varying quantity. It is higher at earlier times than at later times. So if you have this very strict fall-off and a much shallower region as a function of core mass, even if you have a completely flat, featureless underlying core mass distribution, you will end up with the relative deficits and excesses in the sizes of the planets. That's exactly what we see to the right. All I've done here is I'm setting some sort of an underlying core mass distribution, and I'm just drawing from the left curves over here. The unfilled histogram is the flat underlying core mass distribution. The filled histogram is where we made the correction at the high mass end, because in the radial velocity follow-up to the Kepler planets, we do see the fall-off in the number of planets beyond around 10 Earth masses. So that's all I've done here. Now, what exactly is going on shaping all these peaks and valleys and fall-offs? This huge peak over here, these come from those more or less rocky cores. So they fall below about 10 to negative 5 over here. Really thin atmosphere, the sizes are dominated by the cores. And the size of the core scales with the mass to about 1/4 power, which is a very shallow slope. So that's going to show up as a relative excess. Once you go above about 10 to negative 5, but you're still in this isothermal limit, you have such a limited dynamic range to fill up that space, that's going to show up as a relative deficit and therefore a gap. Once you transition to this much shallower cooling curve, much wider dynamic range to fill up that space, so you have a peak until a fall-off due to just the fact that we don't have that many massive cores. So let's compare this with the observations. We do see some hint of an increase below about an Earth-sized object. We definitely see a gap between around 1 to 2 Earth radii, isothermal gap between 1 to 2, peak between 2 to 3, peak between 2 to 3, fall off beyond 3, fall off beyond 3. Without any mass loss, just from gas accretion. Furthermore, this transition between the isothermal to cooling curve, that is what sets the location of the radius gap. And it varies as a function of orbital periods. As you go closer and closer towards the star, the disk gets hotter. And with the hotter disk, the bonding radius shrinks. That would shrink this isothermal mass, and that would effectively push this transition to the cooling curve towards the right, towards more massive cores, and therefore slightly larger radius. And this is good news because we do see this in the observations. In the radius period space, this gap, the location of the gap is slightly larger at shorter orbital periods. The slope is negative, in other words. Comparing this to the model, we have 2 different panels here. Those just correspond to different ways in which we treat the bottom of the core mass function, because at the moment it's completely unconstrained. Regardless of what we do to that bottom of the core mass function, we robustly reproduce this radius gap with that negative slope. Even at the more quantitative level, this agrees very well with what is reported in the observations. This is the same plot with the sample limited to the astroseismological characterization so that we have more precise measurements on the size of the planets. So within 1 sigma, we have a very good agreement on what exactly the slope of this radius gap is, just from gas accretion. So what this means is that some of these planets are just born rocky, and then they just stay rocky. So if we can create this radius gap primordially before any sort of mass loss very robustly, then does that mean that mass loss does not happen? Well, I would say that probably that's not the case, because it's actually really hard to shut off, especially the photoevaporative mass loss. So instead, let us try to see what happens if we take this population and process it with the post-formation mass loss. So at the top, this is formation. At the bottom, this is taking that with the evaporation. The upshot is that the gap morphology is more or less largely maintained, with the expected difference being that you do have the transformation of the short period gas envelope planets to short period rocky planets. But the degree of the change is not enough to make a drastic change to the shape of this radius gap. And in fact, with this primordial radius gap and accounting for the evaporation, you can also reproduce this long period rocky planets. So I would say the origin of this radius gap is likely primordial, but then the aftermath of that, the mass loss processes, likely further sculpt the population and give out some sort of second-order effects. So if that is the case, how can we test whether what we see as this gap really has the primordial origin? So one way to do that is, and these are all difficult, but we do need a better characterization of this long period small planet occurrence rate. I did mention that we do see some evidence that they exist and may even be dominant, but it's right at the detection limit of Kepler. So right now, depending on your favorite statistical methods, you do get different results. So we really do need more data to try to fill up that space to the right. And one mission that could probably do this is Plato, especially if it gets an extended mission. We may be able to really answer this question. And if we do see the evidence of their existence and may even be a dominance, then this would be a positive test towards the primordial origin of this radius gap. Now, we've been talking about the size and the periods of the planets, but there is a third fundamental observable when it comes to exoplanets, and that is the mass of the planets. And I would say the radius mass space is actually a better space to distinguish between the primordial population and the evaporated population. So here, in the contour lines, those are model. So the orange is for formation. Green is taking that and let them undergo the evaporation. Comparing against data with the circles over here, Those are radial velocity measurements of the mass. There are triangle points. Those are transit timing variations. Top to bottom, cores that have assembled slightly early, cores that have assembled slightly late. So in general, if you want to create these puffy planets, you do require early core assembly. We've already seen this when we discussed gas accretion physics. In order to create these mini Neptunes, you do require late core assembly. We've also seen that before. These population, these are the super Earths with the mass measurements, and those are really hard to create just from formation. They are probably the photoevaporated mini Neptunes. And we should keep in mind that the super Earths with the mass measurements is only about 10% of the total population, and because of that bias towards measuring the more massive objects, it could very well be the case that these are sort of like tail-end population of the super Earths. In fact, in the model, we do expect more of a skewing of the mass distribution towards the left, so towards the smaller masses. So another way to test this theory is to have more mass measurements of these small planets to see if we can really push this towards the left, to see whether the mass functions of these planets are really truly pushed more towards the left. It's more skewed towards the bottom of the function, or whether these populations are representative of the total population of these small planets. And for this, there are some extreme precision radial velocity instruments that are being commissioned or in operation that could potentially give us a bit more data points over there. And if you're just concerned with the mass function, then actually Roman, especially with the microlensing component, would be uniquely capable of giving us the constraints on the bottom of the planetary mass function. All right, so those are for small planets. Let's now talk about the large planets. And I'd like to start by making a population level comparison between the small and the large planets. What I find really striking about these two differing populations is that when you take a look at something super simple, like the distribution of the orbital periods, already you see a drastic difference. These small planets look very flat, which means there's no preferred location for these planets, at least out to 300 days. And if you're wondering what's going on with the break, you can explain that by realizing that these disks in which the planets form have some inner edge, given by the magnetospheric truncation of the star. So if you draw from the measured spin periods of pre-main sequence stars, you can explain both the location of the break at around 10 days and the shape of the fall-off. For our discussion, it's more important to look at how, for large planets, it just continues to go up. And in fact, with the long baseline radial velocity surveys, we see a statistically significant peak at a few AU. So giants have some preferred location between 1 and 10 AU. Why is that? What is so special about that location? And for this, let's go back to these 3 key properties, and let's now talk about the effect of metallicity. As a reminder, less metals, less opaque, easier to cool, easier to accrete. So does that mean that within the protoplanetary disk, there is some special location where we see a local minimum in the metallicity of the gas that could be accreted onto these planets? And in order to answer that question, we're going to trace those metallic species with grains and draw some radial and vertical gradient in the dust-to-gas ratio. The reason why we expect that is because the grains and gas interact with each other. So that's a gas parcel, that's a grain. The gas parcel feels the stellar gravity, but there's also oppositely directed pressure gradient force. That means it's going to move at a sub-Keplerian speed because the effective potential is lower, while the dust grains move at a Keplerian speed. And the net velocity, the relative velocity between the two, means the gas will drag on the grains, sap away the angular momentum, and cause some radial drift. But this degree of the drift is very sensitive to the size of the grains. If the grains are too large, then it has high inertia. This grain will not care about the drag. On the other end, if the grains are too small, then this drag process can quickly erase away this relative velocity between the two, and that will shut off this radial drift by definition. In other words, these grains are way too well coupled to the gas, and it'll just flow with the gas. So there's an optimal size for the drift given by where the frictional stopping time, so the time it takes to reach the terminal velocity, is on the order the local orbital time. For those of you who study dust dynamics, that just means Stokes parameter being of order unity. So as the dust and gas interact with each other, the dust grains themselves also interact with themselves by collision, for example. And if that collision is energetic enough to exceed the material strength of the grains, then they'll likely fragment. If it's not energetic enough, probably there's some degree of growth. So let's combine all this together to see what we should expect as the radial and vertical gradient of the dust-to-gas ratio. And I should start by saying that this was a work led by Yayati Chachan, who was a recent graduate from GPS at Caltech, and I'm very happy to have him in my group as a CETA National Fellow. So this is a disk. Let's start from outside in. At the very outskirts of the disk, there's barely any action because the dynamical timescales are too long. But as you go closer in, then the drift of the grains catches up. And in fact, at these locations, the drift is faster than the growth. So that means in these regions, you will have a draining of the dust and a decrease in the dust-to-gas ratio. As you go inside around 10 AU, then the growth and fragmentation will catch up. But when it comes to growth and fragmentation, there is a special location within the disk called the ice line, where beyond that, the disk is cold. It's cold enough that you expect some icy mantle forming on top of these grains. On the inside, the disk is hot enough that you would expect the sublimation of this icy mantle, and you have bare silicate grains. And in these disk environments, those silicate grains are more brittle. So you'll have more fragmentation, smaller fragmentations, more coupled to the gas, therefore less drift, and a pileup of the grains in this inner region. With more careful calculation, indeed, we do find the overall decrease in the dust-to-gas ratio and a pileup on the inside. So that's the radial profile. What about the vertical profile? And we need to know the vertical profile as well because these planets have some limited reach in their capability to accrete the gas, given by the minimum between the Hill and the boundary radius. Notice how there's a vertical uniformity in the inner region and much more of a gradient in the outer region. The reason for that is because there is a competition between the turbulent diffusion that mixes up all these particles and the gravitational settling that tries to collect all the particles at the midplane. And in the inner disk, we have dense gas. Particles are more well coupled to the gas, more well coupled to the vertical turbulent motion, and therefore vertical mixing. On the outside, you have sparse gas, so particles are less coupled, and they're more likely to settle down due to the vertical component of the stellar gravity. So that explains this difference between the two. In terms of this curvature over here, that just reflects the radial gradient that we have just discussed. Notice how there is this special location between 1 and 10 AU where we have this minimum in dust-to-gas ratio that is within the reach of these planets. So combining that to the gas accretion calculation that we have discussed earlier, we do find that, given all else equal, giants are more likely to form between 1 and 10 AU. exactly coincident with the peak in the giant occurrence rate between 1 and 10 AU. Okay, so we began our discussion by looking at this huge diversity in exoplanetary population, and we have identified 3 key parameters that control what kind of a planet we would end up with. When the core assembles, how massive that core is, and the opacity of the accreted gas. And using those parameters, we have zoomed into individual classes of planets to look more carefully at some of the measured trends and patterns, like this radius gap that separates the rocky planets from the more gas-enveloped mini-Neptunes. And we've seen how, even before any sort of mass loss, just the primordial gas accretion can robustly carve out this radius gap, with further mass loss giving some second-order effects. And how can we test that? We do need better characterization of the long-period small planet occurrence rate. If we do see that they exist and may even be dominant, then that would be a positive test for the primordial origin. We also need more mass measurements of the small planets. If we find that the mass function is very broad, maybe even bottom-heavy, that's another positive test for the primordial origin of this radius gap. And for the gas giants, we've seen this observed peak in their occurrence rate between 1 and 10 AU. And this can be naturally explained by the combination of the dust drift and growth that creates a local opacity minimum, and therefore a favored spot of Jupiter formation exactly between 1 and 10 AU. So what are some next steps that we could take? Of these 3 parameters, by far, it is the mass of the core that is the most critical in terms of setting the final size of the planets. But we don't really have a complete understanding of what we should expect as the mass function, the core mass function, or even just the mass function of these planets. So one thing that I would really like to do, sort of my near-term goal, is to build some predictive model for the planet mass function over time and orbital distances by following the mergers between the smaller protocores, like building a merger tree. And in particular, I would really like to fill up this blank space over here, which I think is a timely endeavor because of, as I mentioned, the Roman, especially the microlensing component of the Roman mission, has this unique capability to go all the way down to the sub-Earth mass regime, thereby constraining the bottom of the planetary mass function exactly at this intermediate distances where we currently have this blank spot, but it is also the region where we see our solar system planets. Taking a step back, though, a lot of the planet formation theories so far have been focused around sun-like stars because, well, we live around the sun, but also because a lot of the prior observations have been focused around sun-like stars. But thanks to TESS, Gaia, and ground-based spectrographs, we now have better and more precise characterization of the planet-hosting stars, as well as access to those planets around these different kinds of stars. So one of the sort of major research direction that I'm taking in my group is to quantify the formation efficiency of these different classes of planets as a function of stellar age, metallicity, spectral types, and even galactic environment. And thereby to draw and build a more complete galactic census of these exoplanets. And taking an even bigger step back, I mentioned at the very beginning of this discussion how planet formation begins from the formation of stars. So then, can we try to chart this full trajectory of planet formation from those very early stages, sort of the late-stage star formation, early-stage planet formation, all the way to the final planetary systems? For example, even for something really young, like class 1 disks, it's a bit hard to see here, but there is some evidence that those young disks have some substructures. So does that mean that the planet formation happens really early? or is it simply a reflection of dust gas dynamics due to that surrounding turbulent medium feeding these young stellar system? And starting from this ringed protoplanetary disk at a T-Tauri phase, can we directly follow the size and spatial distribution of those grains locked into those rings from the gas-rich protoplanetary phase to the gas-poor debris disk, and try to see whether there is some unique feature that we can find that can trace back to the potentially perturbing planet as well as the secondary planet formation. And starting with those dust distribution, with those young planets, those planets can dynamically perturb these debris disks, giving unique morphological features over multiple wavelengths from optical to radio, which can help us constrain the planet population at those wide orbits all the way down to the super-Earth mass regime that are otherwise invisible to modern detection techniques, and thereby drawing this direct link between the birth stages of planet formation to the final product as presented by the exoplanetary population. Thank you.
We have time for a few questions.
Thanks for the talk. As you know, I work in young stars and star formation, and so we have the same fuzzy concept of a core. And so I was trying to pay attention to your N gas and core ratios that you have a plot where you're delineating the different regimes. And so I'm wondering, is there a definition for a planetary core? Define the x-axis.
How do I define the x-axis? Right. So it's basically some massive object where it is massive enough so that you can actually accrete gas. And the way to define that is to make sure that its boundary radius is larger than its physical size. And the limit for that is around like series. If you fall below that, then it makes no sense to say it's like a planetary mass function within this diagram because you cannot define the gas mass.
How can you form a planet late? So you said these planets with small atmospheres can form without atmospheres because they form late. But if you form a planet in situ and you have enough mass to build it, you do it very fast. It can take 5 years at this orbital period. And if instead the planet migrates from further away, well, you have to give some time for it to migrate to the place where you observe. So I don't see how anything we observe so close to the star could have formed late.
Yeah, that's a great question. So I think this is a question of where do you set time equals 0? So like I set time equals 0 as when you start accreting lots of gas. And the idea here is that you can create small objects very early on, and you can also have them migrate. But if you want to build something like a few Earth mass cores, you need some merger processes. And in order to have those merger processes, you actually have to wait a bit, because if you have too much gas around, then all those dynamical friction will circularize all the orbits. So you actually cannot have mergers. So you are going to just have like small objects sort of like all circling around. But like once you can get rid of all the gas, you can have more of dynamical instability, more mergers, and therefore the final core products. So that's really what I mean when I say late formation. It's not like from the very beginning that's late. It's more like what is the final assembly that allows us to have this final gas accretion. Yeah. Actually, so within this plot, it would be 2, 3, 4. It would be like right over here. Yeah. So it's basically like drain the runaway, but then you actually don't see the feature of, well, it's sort of a combination of the runaway because it's steeper, so it's going to show up as like a deficit just just by analogy of this like steepness giving the deficit. But also on top of that, we just don't have that many cores. But that comes from the observations. So that's also what I mean, that like we should really try to get a sense of like why, what is so special about that 10 Earth masses, why do we see a fall off? Yeah, another great question. So I think this fall off can also manifest, but in terms of, I think you might also need like additional mass losses. So for example, if you go back to the this plot. So if you just like look at this like subsaturns at those short periods, it falls off. So it falls off. So this like falling off process, you can actually explain this fall off slope from mass loss. So even if you start with a completely flat sub-Saturn population, those are pretty puffy. So you can allow them to undergo mass loss processes at their short orbital distances, and that is enough to actually carve out this slope. And actually, what's really cool is you can use that to constrain what the expected core mass distribution is for the sub-Saturns. And the idea is that, well, at any given orbital distance, you can define some critical core mass that safeguards it against the mass loss. So, I mean, planet occurrence rate, you can take it as a probability distribution. So if you have a core mass distribution, and then there's some critical mass range where above that you survive and below that you don't, then the probability of sort of like integrating that probability distribution at the high mass end directly translate to the occurrence rate of the planets at that orbital period. And if you do that, then that exercise gives a very good agreement with the sub-Saturns with the mass measurements.
Any other questions? Yes?
What do you think the distribution for F would be in this problem?
Distribution for
F-like planets.
Earth-like planets?
Yeah.
Oh, yeah. It's my guess is that it probably follows the black curve. Yep.
All right. Any other questions? Last call? If not, then let's thank the speaker.